Good morning to one and all. I'm Tanisha Neelam Das, Manager Administration and Examination from the Indian Institute of Metals. It is my greatest pleasure to welcome you all to the webinar, The Role of Additive Manufacturing in Transforming the Aeronautical and Space Industries, which is co-organized by Indian Institute of Metal IIM and the National Additive Manufacturing Innovation Cluster NAMIC. A survey by Willis Associates revealed that aerospace applications make up one of the leading industry sectors served by 3D printing companies. This growth is likely due to the demand for lightweight parts and components made possible with additive manufacturing. In recent years, we have witnessed disruption in the space industry brought about new technologies, including non-traditional hybrid propulsion engines and 3D printing rockets. Meanwhile, the aviation industry has seen an increasing number of qualifications for 3D printed materials and components. With growth in this industries, let us dive deeper into the applications of additive manufacturing in aerospace. First, let's go through the agenda and see what is in store for all of us today. First, we have the opening address by Amol Gokhale, former president of Indian Institute of Metals, followed by the opening address from Mr. Marc Lee, head of IP and Commercialization of the NAMIC. Then, Dr. Deepa Srinivasan, chief engineer, Pratt & Whitney, will share the successful qualified applications of additive manufacturing for gas turbines aerospace. Next speaker, Mr. Ali Baghchehsara, President Plasmos, will share with us the role of 3D printing in advanced space propulsion. After that, challenges in induction of AM components in aerospace applications will be shared by Dr. Govind, Bajargan, General Manager, Vikram Sarabhai Space Center. Mr. Gene Miller, Technical Sales Engineer, Velo 3D will throw some light on achieving the manufacturing milestones needed to succeed in space. Last but not the least, to round up this session, we have a 45 minutes panel discussion on disruption and growth with additive manufacturing. What does this mean for the aerospace industry in the next decade? Which will be moderated by Mr. Marc Lee. Our audience may ask questions to the speakers during the session via Q&A box anytime during the webinar. Without further ado, it is my pleasure to invite Dr. Amol Gokhale, former president, Indian Institute of Metals, for the opening speech. The Indian Institute of Metals is a forum for metallurgical and materials professionals. The institute was founded in 1946 and serves industry, R&D, and academia engaged with metals and materials. The scope of industry activities include minerals beneficiation, extraction, fabrication, heat treatment, finishing, as well as practical and theoretical aspects of metallurgy of all ferrous and non-ferrous metals and alloys. Ceramics and other disciplines and technologies aligned to metallurgical problems also come under the scope of the Institute. The activities of the Institute include organizing national and international technical conferences and programs, research activities, publication, conducting qualifying examinations, etc. Dr. Gokhale did his BTech in Metallurgical Engineering from IIT Bombay in 1978 and PhD in Metallurgical Engineering from University of Pittsburgh, USA in 1985. He served in the Defense Metallurgical Research Laboratory, DMRL, Hyderabad, DRDO from 1985 till 2015, where he was the director of the laboratory. In August 2015, he joined the Indian Institute of Technology, Bombay as Professor of Mechanical Engineering. He has vast experience in aerospace materials and processes and has worked on additive manufacturing of aerospace alloys. He is currently the chairman of the steering committee of the Aeronautical Research and Development Board and chairman of extramural funding program on gas turbine materials and processes. He was the president of Indian Institute of Metals in the year 2021 and is instrumental in bringing IIM and NAMIC together. Mr. Amol Gokhale, we welcome you to the webinar.
Thank you very much, Tanisha. And let me welcome the delegates who are participating in the very first IIM NAMIC joint event on the role of additive manufacturing in transforming the aeronautical and space industries. So why are we interested in this topic in India? India has a strong presence in the space and aeronautical sectors. There is a well-established satellite program, as many of you may be knowing, which covers development, production, deployment, operation, and application of satellites. The ISRO has a lunar mission as well as a Mars mission. It aspires to put humans in space in the near future. And it also has an upcoming program to study the solar surface and development of various vehicles to enable such studies. India also has a large fleet of aircraft, both in the commercial and the defense sectors. Although the civil aircrafts are of foreign origin, they are maintained, repaired, and overhauled to a great extent within the country. All the Indian Air Force aircraft are completely maintained within the country. It has its own indigenously developed, produced, and now inducted fighter aircraft called Tejas, LCA Tejas, and a light helicopter, which is also under production and in induction into the Indian Air Force, and several unmanned aircraft for reconnaissance purpose. Moreover, there are many young entrepreneurs who have startup companies developing rockets and other satellite hardware. Now, such a big sector cannot be without a strong R&D network, and India has a very strong R&D network engaged in aerospace research, which includes the Indian Space Research Organization, the Defense R&D Organization, various laboratories under the Council of Scientific and Industrial Research, which have been mandated to develop aircraft for regional transport within the country. And also there is a research and development board, which was just mentioned a while ago, called the Aeronautical Research and Development Board, which funds extramural research at academic institutes as well as R&D laboratories, which has been supporting various technologies, including additive manufacturing technologies for the benefit of the aeronautical sector. The aerospace industry stands to gain from additive manufacturing due to the short lead times to deliver the first article and the ability to adapt to changing designs during the developmental stage of various programs. The possibility of embedding sensors within the components also creates possibilities of integrated health monitoring of aerospace vehicles. I'm happy to see that the focus of additive manufacturing has been shifting from simple prototyping maybe 25 years ago to understanding the microstructures, defects, residual stresses, dimensional accuracy, properties, and more recently to product certification. Aeronautical industry, as we know, has some of the most stringent quality requirements and moreover elaborate certification procedures. There are challenges, at least in the Indian context, about the availability of the feed materials, namely the powders and wires of the right quality with regular supply chains in place. Also, the process yield is a matter of concern which can affect the commercial prospects of the technology. Our institute, that is the IIM, is presently looking to expand its horizons in collaborating with professional bodies in other countries. In 2021, last year, IIM participated in the European Metallurgical Conference, which is a flagship event of the German Non-Ferrous Metal Society called JDMP. Recently, we also signed an MOU with the Japan Institute of Metals, and we will be participating in the upcoming annual fall meeting in Japan in September this year. We also have in pipeline an MOU being signed with the Material Australia very soon. Lately, IIM has decided to broaden the scope of its domain areas to include manufacturing in a big way. since the subject is quite inseparable from that of materials. Consequently, we opened a dialogue with NAMIC about 18 months back and sought a joint event, potentially leading to a long-term understanding between the two bodies. IIM has a wide experience in materials, while NAMIC's expertise lies in manufacturing, additive manufacturing in particular, and we thought there lies the complementarity between the two organizations. We could not have expected to get a better team of speakers from the Indian Space Research Organization of India, Pratt & Whitney's Tech Center in India, and two well-known companies from the US, namely Plasmos and Velo 3D, which are in the business of additive manufacturing. I'm indeed happy to see such widely experienced speakers today. No collaborative activity happens without sustained efforts by a few committed individuals. And I would like to thank Dr. Kandukuri Shastri, who was in Singapore till last year, who led me to Mr. Mahendran Reddy, who was with NAMIC till recently. And both Dr. Shastri and Mr. Reddy are in Europe. However, they have played key roles in bringing IIM and NAMIC together. Also, I would like to thank Dr. Shrikant Joshi from University West Sweden, who is with us today for much of the planning and organization of today's event. Without taking any further time, let me wish this joint event great success, and let me hand over the baton to the MC, Ms. Tanisha Das. Tanisha, back to you.
Thank you, Dr. Gokhale. Now I would like to call upon Mr. Marc Lee, Head of IP and Commercialization from the National Additive Manufacturing Innovation Cluster, otherwise known as NAMIC, for his opening address. NAMIC is a Singapore government platform initiative to catalyze innovation and scale industry adoption of digital additive manufacturing technologies. Since its inception in late 2015, NAMIC has raised millions in public-private fundings to catalyze various AM initiatives across several industry sectors. As of April this year, NAMIC is now a national platform hosted by A*STAR, the Agency for Science, Technology and Research. With closer proximity to the dedicated research efforts in Singapore, NAMIC is hopeful that this move will bring forth greater acceleration in the adoption of AIM across industries. Mr. Marc Lee heads the portfolio of Head of IP and Commercialization at the National Additive Manufacturing Innovation Cluster, NAMIC. He concurrently leads the industry consortia cluster of APAC ASTM Center of Excellence. Before this portfolio, Marc spent 10 years with the Forbes Global 2000 company with various portfolios from technology management, project management, and marketing. Marc was also materials engineering graduate, and he also had held engineering roles in aerospace companies from the Fortune 500 list of companies during his early careers. Mr. Marc Lee, we welcome you to the webinar.
Thank you, Tanisha. So very warm welcome to everyone for the webinar, and I'll run through the program that I'll be sharing very shortly. Basically with a corporate introduction of NAMIC, followed by a short explanation on some of the funding programs, and rounding off with a description of the ecosystem in Singapore. So a little background about NAMIC. We are a national initiative now currently led by A*STAR and supported by the National Research Foundation in partnership with the Economic Development Board of Singapore and Enterprise Singapore, together with A*STAR. So we seek in making the industries competitive through making strategic plans for the future of manufacturing and pushing for public-private collaborations. So this is done through nurturing and expanding the AM ecosystem by pushing for creating new platforms to test and implement business models and growth, and also accelerating AM standard creation. So being a business regional hub and transshipment hub, we aim to build a global ecosystem of research and industry players to develop AM, whether or not they are involved in the current ecosystem. So this will establish synergies with the various partners, bring in new companies, which will allow translation and commercialization of these various EM technologies. So in Singapore, we have a very vibrant public EM ecosystem. So Singapore's network of IHLs and RIs might not be as extensive as other countries, but what it lacks in numbers is made up by the level of funded activities by all the EM centers. So between 2016 to 2020, NAMIC alone funded more than 200 public-private initiatives. We've deployed hundreds of research performers to perform R&D that's meant for industries and company needs, and encompassing more IHL tech depots, which increase its bandwidth and ability to meet the industry needs. So all this actually ensures very timely, well thought through usage of AM resources, and also better coordination of the translational research activities, which is critical for industry adoption. So as part of the technology translation and industry applications, NAMIC helps to mature the technologies from anything as upstream as software development, design optimization, down to the material characterization, equipment characterization, and most importantly, the post-processing. So standards development is also another area which is strategic for the various domains, because only through standards development, the demand by end users will increase, and correspondingly, the supply will increase and the price for AM will drop. So NAMIC has also engaged in multiple industry partnerships. The main aim is to coordinate and translate such public sector R&D efforts, and eventually it will scale the industrial adoptions. So the outcomes, which actually highlights all the various qualitative values that we have created across various startups, enterprises, and MNCs. So the following, you could see the progress within the EM ecosystem from sectors such as M&O, maritime, biomedical, aviation, MRO, and semiconductor sectors. So this actually shows the gradual EM adoption, which is gaining momentum in Singapore. So in order to help the Singapore-based businesses towards adoption at industry scales, NAMIC actually has various funding tiers for Singapore-based companies to perform R&D into these areas. So the three tiers of co-funding actually is targeted at the proof of concept and value validation. And NAMIC is constantly also organizing various events to bring thought leaders and industry together. So pre-COVID, NAMIC would hold 2 AM summits per year. So we will invite international speakers. We'll actually also take part in various exhibitions within Singapore, once in May and once in October, that's part of ITEP. And as well as organizing the Startup Innovation Forum, which was held late last year. It was a very refreshing restart to the MICE events for NAMIC. And we saw a very good turnout and very good interaction during the session. So with that, I've come to the end of my opening, and thank you for attention. Back to you, Tanisha.
Thank you, Mr. Lee. So let's start the most awaited presentation session by welcoming our first speaker of the day, Mr. Ali Baghchehsara, President of Plasmos, who will enlighten us on role of 3D printing in advanced space propulsion. Mr. Ali is an entrepreneur and corporate leader who has a deep understanding in artificial intelligence and autonomous system. He has applied variety of solutions and new concepts in automotive, aerospace, cognitive science branches. Mr. Ali has started 3 companies utilizing AI for the aerospace industry, and also started a venture capital to fund disruptive companies. Presently, he is building a space propulsion company powering interplanetary trips, alongside with advising universities of Richmond, promoting love-based Entrepreneurship, LBE. Mr. Ali, welcome to the webinar. The stage is all yours.
Thank you, Tanisha. I'm very happy to be here tonight for me. Thanks, Mark, for inviting me. It's been always a pleasure to work together, and this time in my new capacity as president of Plasmos. And I also like to welcome all of you. Unfortunately, I cannot see anyone's faces from the audience, which is something I usually have fun with when I was in TV. I was always interested to bring some of the audiences on the stage. Plasmos is a very new company, so compared to some of the presenters who have been in here, the journey of this company is almost only 8 months old, at least as a legal entity. I personally have been very much blessed with having, multiple team members across many countries so far. And it seems like the light went off. Yes, it's an interesting journey to be an entrepreneur in this world. And as you mentioned, Tanisha, let's say the love-based entrepreneurship has been an interesting path that I came to. And having said that, I really love the space. I also really love propulsion. I built more than 200 engines since I have been a teenage, just because I did not have, I hope that the light is somewhat okay. And so it's very interesting to, build a company around something that you have been passionate for a long time. And it definitely creates a different vibe if you are really loving what you do. Not that I didn't love what I was doing in my previous company, Lisa Group, which was an artificial intelligence / cybersecurity firm. But tonight I'm here to talk about future of a space, to talk about future of Cosmos, and basically understanding where we are at. The first slide that I want to start with is Control P rocket engine. So yeah, this picture is from Relativity Space, and this was my initial start. So this picture, what it really shows is one of the first rocket engines and the tanks that are being printed with a very fantastic company that I really appreciate their efforts and their team members. In fact, one of their first, I think he's their first employee that was recruited, John Rising, has joined my team more than 10 days ago, and he's helping us also to figure out some of the challenges we have been facing. So having said that, I want to talk a little bit about what is it that we are actually doing. We are building a new class of propulsion system. I personally am a believer that many of the propulsion systems that we are using today are designed very, very long time ago, and almost too long. And that basically has advantages and disadvantages. The advantage of it is that we know everything about them. Not everything, but many things, enough to maintain them, build very reliable engines that we are using, whether in the fighter aircraft industry or whether in commercial aviation or other industries. And so the disadvantage is, however, that we are relying on certain fundamentals that has been built and designed in the 60s and the 70s and the 80s, which I believe needs a change. And so one of the steps that Plasmos as a team is making is to combine chemical and electric systems, which are fundamentally two different systems today. So chemical engines, like the engines we know from Space Shuttle, we know from Raptor, from SpaceX, and other companies. They are basically, chemical engines, and there are other type of chemical engines like solid engines. But electric propulsion has been rather a new realization in terms of its capacities, being practical, being on satellites from Astrium in 2009, which was actually led by another team member of mine, Alan DeMeyer, at the time, or systems that are being launched from the EP side in the last couple of years on OHP, which he was again leading, or also smaller electric propulsion systems that are being used for CubeSats and fairly small satellites. But what we are really doing is to combine these two for a new purpose. The good thing about an electric engine is really that you can maneuver, you can run them for almost 6-7 months, go to deep space missions, and so this is a fantastic thing to have. However, the problem that you have with an electric engine is that, and I'll get to it later on, is that it has a very small scalability. So you cannot scale the thrust of it for so much. It only produces in the order of micronewtons, so much that you can hold the toilet paper still on Earth gravity. But what is the use of making a new type of engine like the one we are making, what we call CLEPS, Combined Liquid Electric Propulsion System? We can use it for actually different purposes, but the main sections that we are using this for is, I would call it creative launches. So these are basically launches like a spin launch, one of our newest to be partners that they launch, or basically shoot a bullet, I would say, very fast to space by a centrifuge effect. So they basically rotate a rocket so fast and then let it go out of that pipe, what you see on the left-hand side, so that it goes up to 70, 80, 90 kilometers. And then we are coming in the game to say, okay, we can take it from here and go to a further destination, whether that's LEO, MEO, or GEO. So let's say go beyond. In second stage or third stage, so from a normal, typical standpoint of a launch, when you go to the lower Earth orbit, you want to go to higher orbits. That's also an engine that can be useful there, just because it produces in the certain order of thrust, like from 1 Newton to 25 Newton. I'll get to that as well. And of course, deeper space, which is more and more interesting every day. However, the market for that is very limited today. As I said, market, I want to talk a little bit about that as well, because I feel, of course, academic funding and things are always tied together, but there's a new page that has been browsed just not really too long ago, talking about more than 40 billion investments per quarter to the space economy. It's a huge number, $400 billion space economy annual spendings just today, and more than 3x expected growth by the next decade. These are numbers that, you know, maybe we see once in a while, but in an industry like a space, it's really taking a turn and a speed. And this speed is a little bit different than what NASA has been doing a long time ago. So I would say that the big difference is started or maybe accelerated by some efforts from Elon Musk, like adding an economical angle to it, to say, well, we want to go to space, but we want to go there cheaper. We want to go take reusable rockets. And now the very recent developments are looking at it from a mobility standpoint, whether that is, you know, moving from one orbit to another, the satellite buses that take one satellite, go to another orbit, raise an orbit, add fuel to it. These are all aspects of a mobility, what we see in cities, where we say, I need to have a gas station, I need to have certain things go around, have a taxi, have a bus. These are angles of a mobility that is now being created and accelerated in the space business. And of course, also, you know, the satellite and launch vehicles are in an extremely fast inflation point. I want to now switch gears and go back to what I was trying to tell you earlier, just in a graphical sense, to say what is it that we are targeting to build in our rather young company. Electric propulsion is probably familiar to at least most of the panelists here, with a high efficiency, low fuel consumption, and of course low thrust, or as I said, AKA puff engines. Some folks call it that way, and I actually like it. Chemical propulsion is on the other side, larger scale thrust, so you can really have tons of thrust to take something to the orbit, but they are inefficient. Averagely 300 seconds ISP can be high. It can be even higher, 350. But really, you cannot really go that much higher than that practically. So this fuel demand is really annoying when you want to talk about, okay, I want to use my satellite to go to another orbit, constant refueling with a fuel that is not really available. However, in electric propulsion, you have access to, let's say, the solar panel. So what we are trying to do is to combine these two. Of course, I cannot get into so much detail of how we are combining these two things. There has been quite a long time of research despite the just 6 months operations of the company. Even some of my team members have been working on this more than I have been alive. So it's definitely an interesting journey to start and take practical steps very fast. And just to give you some key performance indicators, more than 700 ISP is what we are targeting to create, more than 1 Newton of thrust versus 5 micronewton. Sorry, micro is a word missing there in the electric. Electric is even written wrong. But the complexity of producing such an engine is extreme. I wouldn't say I or my team are the first ones to try out this, but we are definitely the first one to try it out this way. And by this way, I'll get more into it. But our engine has many layers into it. I'll get a little bit more into it. So you can just see a little bit of this from the coils that are inside, from the a specific cooling system. We cannot take the cooling systems and the methods even that you can really cool the entire engine of a normal rocket system as it is being done on B4 engine, on Relativity's engine, and many others. We have to really take a different approach on those things. Not that I know of those details, but very specifically, we cannot have a symmetric cooling system just because we have a very high temperature point at a very specific point of this engine, and that is just more than 1,000 times hotter than anywhere else in this engine, which is making a manufacturing of it, making the cooling system very weird. So just one more thing that is also, considering the cost of productions and operational aspect of a company, but also operationals of this engine, we are intending to have this engine made in a way that you can operate it more than 24 hours. Given that every spacecraft is different and manufacturers in the space industry are doing everything more or less vertical, we want to break into that vertical integration standpoint. So we are making a flexible system. What you see on the right-hand side is a mobile interface, which we may realize sometime soon on a system that people can really select to say, this is the thrust range I need, and this is the power availability I have. So our customers can really come up and give us their system, their requirements in a very easy manner. And of course, then they can see the characteristics they can get in terms of weight, height, their range, and some more details. This is just an example. And so those are the kind of things we want to have. When you want to talk about production, the traditional ways in CNC pressing, even a small materials, a small tubes, it's going to be extremely difficult if you want to scale for every single client up and down. But when you talk about additive manufacturing, things become slightly different and hopefully easier as we are entering production right now. We have also multiple materials, which is another topic for us. And of course, we want to have these engines made nice and high quality, affordable, but also reliable. So I mentioned some of this layering. I just want to give you what do I mean. We have a high voltage. I mean, when you go to some facilities and there is a nice sign there that says danger, that's not going to end there for us. We have to really build isolations in there. Mark and I have had interesting conversations overnight about what are the technologies that are available, what kind of material can be used on top of the things we want to print in super alloys, because that's not going to be electrically resistant in terms of, so that we can isolate things. We are going to have coils inside the engine because we have to have a magnetic field. There is, as I said, one point that just to give you, a rough estimate, we are going to have more or less as much as thermal pressure, as much as that you can imagine 3 guys sitting on one piece of plate and just making arcs there and welding something. That's as much that we have on a very small fraction of our engine. So cooling it is extremely challenging and very different. Our cooling system, when some of the experts look at it, they are like, geez, this looks really weird. And of course we have multiple layers of different things. So it's basically 2 engines made in one. That makes the production, of course, very difficult. However, we have came a long way. What you see on the right-hand side is the first prototype that is coming alive. In fact, I saw Genius talking today that I initiated the conversation to Mark to invite the guys from Velo, because I really loved what their company was doing. And for a fact, they decided to have their CEO, Benny, has a good intention to our company and moved some needles for us in some good directions, which I'm very thankful for, I have to say. And so we will be printing one of our first prototypes with them in a prototype that we can actually fire up and test as well. So just to wrap up some of the difficulties that I was mentioning, the cooling system, the magnets, and both electric and chemical engine. You might have seen, how crazy an engine for rockets looks like. This looks so simple, and yet it has to have all of those elements inside it, because we are looking at it to have it just a lot more integrated, just because we are starting from a green field and not where it was. And as I said, just started legalizing our company more than about 8 months ago, September last year. The 2nd September is unnecessary, but very recently, former CEO of Airbus Defence and Space, a guy that I personally and professionally adore, has decided to join us as a chairman. So we have been making quite fast progress, both in terms of building a team of about 10 to 14 people, both advisors and others, but also really making progress in terms of designing something that becomes a reality and not just a presentation. I remember last year, Deborah Werner, the same journalist that interviewed me, I told her that I want to have a prototype before we start fundraising. And I'm very happy that I could keep that promise as our fundraising just started on Wednesday last week. So it's almost a week, and we have been quite successful so far, raising a couple of safe notes, and we will be hopefully push the boundaries in propulsion for space and going beyond. So I stop here.
Thank you, Mr. Ali, for sharing with us about Control P rocket engines and new class of propulsion system, space propulsion technique, and more. It was very insightful. Thank you so much. Now, our next speaker of the day, Mr. Govind Bajargan, General Manager, Vikram Sarabhai Space Center, is going to share the challenges in induction of IIM components in aerospace applications. Dr. Govind has done his BE Metallurgical Engineering from MNIT, Jaipur in 1990, MTech Materials Science and Engineering from IIT Kanpur in 1993, and PhD Materials Engineering from IISE Bangalore in 2014. He has been working at VSSC ISRO since last 25 years. He is the recipient of INAE Young Engineer Awards 2002 and recipient of ISRO Team Award. Mr. Govind's areas of interest are physical and mechanical metallurgy, solidification and casting, and additive manufacturing of aerospace components. Mr. Govind, we welcome you to the webinar.
So, am I audible?
Yes, sir. You are.
First of all, I'd like to thank IIM and NAMIC for giving me this opportunity. So, topic of my talk is the challenges in induction of IIM components in aerospace. So AM, as you know, it is a incremental layer by layer manufacturing process from a CAD model. So mainly the feedstocks are wire or powder. But the main reason for AM, which has attracted widespread attention, is that it gives the ample design freedom, and that too the complex components can be realized in a very short lead time. Mechanical properties, what we achieve through AM is phenomenal, is equivalent to car, much better than cast components, but equivalent to rod components. Also, it provides ample freedom in controlling microstructures and the material composition. It can increase the performances of the component. So it attracted the attention of aerospace industry. In recent past, the technology has matured good enough that we can get dense parts, defect-free parts in various spectrum of materials, and which gives a good confidence for induction in aerospace sector. It has matured. I can say that it is transition. There is a transition phase. AM is transforming from rapid prototyping to rapid manufacturing, and it is being looked as a reliable supply chain for aerospace industry. The difference what I see in the conventional method and AM is, if we want to exploit full potential of additive manufacturing, in the conventional, what generally happens is that designers, material experts, and fabrication teams are working in isolation. They interact only when there is a deviation seen. But if we want to utilize the fullest potential of AM, all these three teams have to come together. We have to have an AM team, and that is what we saw in the first place when we started inducting AM components in our program. So the strategy what we adopted is that to get the experience of AM and to assess the potential in fullest, we thought, let us go ahead with the existing component and let it be a passive component like brackets, housing, support structures. And the alloys what we selected are the alloys for which parameters are available.
Dr. Govind, sorry to interrupt you, but I think people are not able to see the slides. You may have to put it in the slideshow mode.
Okay, sorry for this interruption. So the strategy what we adopted was to go ahead with the passive components like brackets, housing, support structures, and in the alloys which are well studied through AM. And we carried out the detailed characterization of the process and the materials. So before going into the our plan, let us just see briefly how is the flow chart of AM process. AM process, as all of you know, involves a 3D model and which is converted into .STL format, and subsequently we decide the part orientation, support generation, and slicing of the model, tooth path finalization, then 3D printing, post-processing, and the final inspection of the component. So in STL generation, when model 3D model is converted into .STL format, the CAD model generally contains geometrical and topological information. But STL, we lose the topological information. Only geometrical informations are available. What STL does is it converts whole surface, to triangles, and it is denoted by the coordinates of the 3 points of the triangle, 3 vertices of the triangle, as well as the facet and facet normal. This is the designation. This is how the STL format designates whole model. But in conversion, we have many losses, and those losses generally are taken care nowadays automatically by software. Earlier, it used to be done by manual correction. Once that STL conversion happens, but STL conversion, we lose some information that this is a CAD, CAD portion. Here you can see CAD portion, and this is STL designation. So we lose some information that we call it a chord height. When we go for deciding the part orientation, so in that we generally would like to minimize build time, support volume, and while like to improve the surface quality. So these are the main parameters under which part orientation is finalized. The surface quality is getting affected by the staircase effect. When volume is divided into different layers, it leads to a staircase effect, and it leads to one more error that we call a cusp height. So total error from the CAD model to the final print, we have a cusp height plus chord height. So that is the dimensional error we get. So once the orientation is finalized, we have to build a support. So support means each layer must be connected and supported fully or partially by the previous layer. In many cases, depending on the orientation and all, natural support is adequate. But in some cases, we have to provide extra support, artificial support. So the criteria for here is that it should be easily removable. We should have a less build time and less volume it should consume. Then we go for splicing. The splicing, when it is this model STL format is spliced, the splicing plane generates two coordinates, and for each splicing plane and each triangle, and combining all these coordinates, we get a shape which is to be scanned by the laser. But this straight line connection from point to point connection causes intermittent motion of the laser, which can cause non-uniform material deposition. So generally we go for a curve fitting and to make it smooth. So after a generation of this thing, then we have to go for a tool path strategy. And the aim here is to get a dense product, control microsectional properties, and minimize stresses and the build time. So to achieve all these things on a machine, we thought of there are many references wherein suppose a proposal is to have a benchmarking artifact. So what actually the benchmarking artifacts are? They are generally they help us in assessing capabilities and limitation of AM processes, and then help us in comparing different AM processes and machines. So they are geometrical benchmarking, mechanical benchmarking, and process benchmarking artifacts. Geometrical benchmarking artifact will tell us about the geometrical and dimensional performance, that is tolerances, accuracy, repeatability, and surface finish. Mechanical benchmarking about mechanical properties, and process about process optimization. When we are designing the mechanical benchmarking artifact, what we are looking for is the dimensional accuracy predictions, geometrical accuracy predictions, repeatability, minimum feature size which can be built, and the surface finish. So the idea behind this is that we should have a large number of common features so that we can assess the repeatability and the dimensional tolerances. It should have both positive, that is protrusions, as well as depressions, and it should be large enough size should be large enough that we can call it as a reliable data. We can get a reliable data. Also, it should consume less material and less build time. Also, the features should be oriented in almost all the axes to have assessment based on the direction. There are many proposed artifacts here. So the one which we generated is the last one, and based on that we are trying to assess the capabilities of AM as well as the comparison of machines. Also, based on the location of the build platform, also we can assess whether if we change the location, whether we are losing on any of the dimensional or geometrical tolerances. And it can be helpful in controlling these tolerances by controlling the process parameters. In mechanical benchmarking, when we started looking for, there were two standards which gives us some idea about the mechanical benchmarking. One is that AWS D20/1, which talks about that we should build the coupons, test coupons, at all the 8 corners of the build volume as well as in the center. And it requires building coupons in X, Z, as well as 45-degree direction, and also thick and thin. Thin coupon will be of the order of 1 mm thickness, and thick will be 6.5 mm thickness or higher. So with that, we generate a data based on the location and the thickness and direction of the sample, whether there is any what kind of scatter we get in the property. ACM talks about building 5 coupons at 5 different locations on the build platform along with the density coupons. So what we decided is we optimized that approach and gone for some 25 to 30 coupons along with density coupons. And this one result I am sharing for 316L when around 25 coupons when we printed, we saw that 2 coupons in Z directions are showing lower elongation. Otherwise, properties are more or less consistent. And when it was analyzed, it was found that it has something to do with the one parameter called dosing factor, wherein material powder is added in front of the recoater blade, and the quantity got affected because of some reason. So these kind of things can be cached, and we can address these points if we have a proper benchmarking process. So what we aim is that location and dimension dependence of the effect on mechanical properties can be assessed. Density coupon in each build, whether it is for qualification build as well as the component build, can be added, so that we can get an assurance that yes, the parameters are giving us the required density, and those coupons can be used for microstructure and harness to have a kind of a process check. The third point was the process optimization. So process optimization is a very tricky process, because that the requirement what we are putting here is generally the density, that is 99.5% or higher, the surface roughness 12 micron or better, less porosities, defined fixtures, and no mechanical damage. So the process variables, as all of you know, the laser, powder, and machine dependent process variables are there, but mainly the process variables what we deal with is the power, scan speed, and scanning strategy, that is head spacing and all. So when we went ahead with the building of single track or single wall structures, so on a wide variation of power and scanning speed, this helps us in delineating the zones of lack of fusion, fuel formation, on balling effect. So with that, we can finalize, or we can arrive at the operating window, which can give us a consistent deposit, a smooth wall with a reasonably good surface finish. So then our aim comes in this optimized window, what should be our parameters. So then we have to work on head spacing. There are models available. Here is one model which is written in Python, which helps us in assessing what should be the head spacing with the data like melt pool geometry. If you see the gray color in the model gives us some hint that dark region indicates a lack of porosity, lack of fusion, but the light region, it shows that melting has happened almost 3 times in the zone. So there are zones where melting occurs more than once, and there are zones where there is no melting occur, that is lack of fusion. So by varying the head spacing, we can control the zones where lack of fusion is happening. Here we modeled, and we have shown here that there are zones where single time melting occurred, there are zones where double melting occurred, there are zones where melting has happened 3 times in the process. So once we have this data, now in the optimized window, we have to finalize the parameters. We go for printing cubes in this prism. And based on the detailed study of the density and the microstructure, we arrive at optimized parameters. Just to show the microstructure what we obtained in ALSI 10MG, it is interesting to see that we have a heat affected zone. That this is a fine cellular zone is the melt pool zone, and nearby zone is the heat affected zone in the previous sulfide layer. The intermediate and coarse zone is a partial melted zone, because eutectic melts at slightly lower temperature. So that is where we see a partial melting. And particle zone, where the cellular wall has converted into fine particles, is heat affected zone away from the partial melted zone. If we stress relieve such a structure, we get a coarse particle, but coarsening is higher in the HAZ zone. And when we test it in the Z sample, we'll always see a failure along this HZ zone. So to take care of this, we have to have a proper post-processing plan. That is, heat treatment has to be properly done, and we have to select a proper heat treatment cycle. So here are some properties I am showing you, that where stress relieving is done, we get elongation of the order of 18%, which is never thought of in aluminum silicon cast alloys. And so based on this, then we have formulated our strategy. We have different 4 stages of characterization, that is powder stage, machine and process stage, pre-production stage, and production stage. And with this, stages of processing, we have established kind of a process in our system to induct AM program. Qualification, all AM components to build a confidence goes for qualification test, that is either functional test or destructive test. So I'll just conclude my talk that AM component qualification on aerospace calls for 100% inspection. But there is a need, because the complex component, doing 100% NDT is a time consuming, and it just defy the gain what we have from AM, that is short lead time. So there is a need for statistical and parametric model and real-time monitoring of the system. Then benchmarking is really a good thing, and we can really enhance it in process optimization also. Post-processing like heat treatment and heating and DFAM are really good things which we have to explore a bit. Thank you.
Yes, thank you, Dr. Govind, for sharing with us the flow charts for AM and SLT formats and benchmark artifacts. Thank you so much for the knowledgeable talk. So now we have I would now request our next speaker, Mr. Gene Miller, Technical Sales Engineer, Velo 3D, to throw some light on how achieving the manufacturing milestones needed to succeed in space. Mr. Gene Miller has held various high-level positions in foundry and process engineering. He joined Velo 3D in 2016 as a process engineer, developing unique laser parameters for the company's flagship 3D metal AM printers, and helped elevate Velo 3D's support-free technology. He holds a bachelor's in mechanical engineering from Colorado State University. Mr. Gene Miller, welcome you to the webinar.
Thank you, Tanisha. It's really a pleasure to be here. I'm looking forward to talking about, some of the challenges that we are all faced in the modern day space race. And let's really go through what is holding back the industry from achieving its goals in the modern day space race. So as Ali was mentioning before, there is a lot of new funding and new companies in the modern day new space race that we're all living right now today. There's lots of funds being put into these new launch systems, these satellites and propulsion systems. And the fact of the matter is that they're not all going to make it. Many of these companies have a novel idea. They can, bring a lot of value with a prototype and actually go through the due diligence of finding value added with their novel idea, but then they can't make the jump to production, achieving the goals of actually printing or manufacturing quality parts that can match certification criteria, especially in aerospace and space. And just in the past 3 years, more than half of the funds that have been injected into the industry have just come about recently. So we're on this asymptotic slope of funding that's being injected into the industry. From a Velo standpoint, this is a long list of companies that we have engaged with, have seen benefits in our unique capabilities, and help some of them go to production with a lot of these parts. So Velo 3D was founded in the United States in 2014 by Benny Bueller. That's our CEO standing in front of the Sapphire machine. We went public in September of 2021 under the ticker VLD, really poised to deliver complex, high-value metal parts without design compromise or lack of design intent going into the final application. We really want engineers true designs and optimized ideals to be implemented in their real parts as they're manufactured. Here's an example of some of the parts that we have printed in the past. A lot of them are static and rotational parts. Many are optimized to control flow of fluids and or the transfer of heat, but we're really opening up the design space for what is manufacturable, even more so than just in a traditional laser powder bed fusion system. Here's some examples of things that we've printed before for the aerospace and space industries. This is a thrust, quad direction thrust vessel for the lunar excursion module. This was actually used on the Apollo program back in the 60s, and this part has now been optimized for additive manufacturing. Now, if you take a look at the part, it's manufacturable on a typical laser powder bed fusion system. However, there's a lot of opportunity to do weight reduction further with velo technology. And that's really what we did with this part. We took the traditional laser powder bed fusion part that was printed on a legacy platform and then did further weight optimization and weight reduction to really eliminate all the mass that was unnecessary. And then to maintain structural rigidity, we implemented a lattice structure inside the volume that we extracted. And this was enabled us to print this part with a 67% overall weight reduction without any sacrifice on factor of safety, and also dramatically reduced the manufacturing costs. The original part consisted of many different parts, a lot of assembly steps, and a lot of other sources of failure, to be honest. So this would be practically impossible to machine. If you could machine this, I have no idea how you could do it. Really, this lightweighting lattice makes the machining process impossible. The print itself, if you were to do this on another system, you'd still have challenges with the internal channels. The lattice structure itself would suffer from recoder contact, which Velo3D doesn't have to worry about. Also, the high susceptibility of titanium to cracking. We have an in situ stress reduction technique that ameliorates the risk of cracking in titanium parts. So how do we do this unique printing? We have built a preprint software where we have the ability to detect geometric features, such like bulk and low angles and lattice, and apply a specific laser parameter to print these geometries without the need for support material in most of the cases. So this is all done automatically by the software. The user does not have to be cognizant of these process applications. And this is what you see here, the part that we printed in solid titanium with the very lightweight lattice structure on the inside. Another example is a component for a liquid oxygen pump through Yuzhnoye and launcher. And we printed two components for this part, an aluminum housing as well as a Inconel outlet for the pump. This pump was assembled and tested. The inlet is the aluminum part on the bottom, and the outlet is the portion on the top. This was Inconel 718. And this was tested at cryogenic temperatures by launcher and ran for 2 minutes. And this is a great example of a first article success. Right out of the gate, the pump ran beautifully for about 2 minutes. I won't make us go through the entirety of this video, but here it is starting up right now and then running for approximately 2 minutes until it does shut down. And it was a great first article success for them. They learned a lot without any unexpected anomalies. As well as the pump housing, launcher has printed and is implementing a lot of Velo parts on their orbiter system, as far as thrust nozzles, propulsion and fuel storage, as well as structural components and injectors. They are really utilizing every bit that they can of the optimization ability with the Velo technology. So how do we really do this? First of all, it's not just the printer, it's not just the preprint software, it's not just the process, it's all of these things working together. We designed our own preprint software to apply our own process to the laser print file that is brought over to our own 3D printer. We call it the Sapphire, where the printing actually occurs. Now, this printer has about 1,000 sensors on it, gathering data throughout the printing process, and our quality assurance software, quality validation software called Assure, quantifies all of that in a digestible report at the end of the build. There's also real-time interaction where you can check your print as it's occurring in real time with the Assure software. The Sapphire printer family consists of 3 platforms. There's the traditional standard Sapphire. That's a 315 millimeter diameter build volume by 400 millimeters tall. There's an option to extend that up to a full 1,000 millimeters or a meter. And then the XC is our extra capacity platform, using a 600 millimeter diameter by 550 millimeters tall. And that is actually 8 1 kilowatt lasers, where the Sapphire machine is only 2, but it's still the same optics, same technology, same recoding, same processes. So scaling from the Sapphire machine to the Sapphire XC is rather seamless. So like I said, Flow is our preprint software, and it has the ability to detect unique features and geometries on our parts. As you can see here, the low angle features are recognized, the thin walls, the small holes, the lattice. This is all detected by our algorithms and apply our specific developed laser parameters to achieve printing of these features without the need for added support material. Here's a great example of what we're talking about. We print a lot of rotational components like shrouded impellers. And you'll see the conventional approach is either to fill the inside of this with support material or actually tilt it up on its end, which is a compromise because you are really just kind of pushing the problem elsewhere inside the part, and you're going to struggle with circularity and lack of concentricity when you go to balance this rotating component. The right way to do it is with the Velo solution, where we would print it flat on the build plate. We don't have the need for any support material on the inside, thanks to our unique low angle processes. And after removing a constraining wall around the outside in a simple lathe operation, you can have a unsupported part, and it's still circular and round and able to be rotated at high speed. So these are available alloys available today. Coming soon are copper, stainless steel, and more aluminum alloys. And we have all of our material properties are available on our website. You can go to velo3d.com and download them for free at any time. We also don't sell any of our powders. We don't mark them up. So any of our customers can find their own powder, source their own powder. As long as it is within our spec, it's open source. So Velo3D is one of the few companies that is actually engaging the MMPDS material qualification for aerospace and defense. This is something that we are really passionate about, and one of the few companies that have really tried to tackle this. It's scalable through many machines, and I'll get into that as well. But we are not just looking at qualifying material that comes off of one machine. We're trying to do it for all machines across our fleet. And the idea of the golden print file is something that Velo3D does that is very unique in the industry. We have a scrupulous qualification process, as well as active tool health checks that are ongoing to ensure that the machine is functioning nominally and able to print the desired outcome with one single print file. And I'm not just saying that we can do this, we're actually doing this with customer parts today. We create one print file and send it to multiple customers, and they print that file with the same result. So this is actually being implemented today. So to sum up real quickly, we really want to enable our customers to focus on the solution, not get lost in the manufacturing headaches and the really shortcomings to really make compromises in their design. Even on the most advanced aerospace geometries, where optimization is key and you really need to push the boundaries of what is manufacturable, we really want to open up that design space. We want to adhere to the strict aerospace standards for material properties, hence our involvement with MMPDS qualification and certification. We, like I mentioned before, the fleet level standardization of processes and calibration is some of the best in the industry. We're not brushing problems under the carpet. We don't have dead zones on our build plate. The flow is characterized. We're really trying to solve all the problems and not really brush anything under the carpet. The processes that we would engage a customer on are going to be the identical process that we would use in production. So again, the scalability there is really seamless to go from development to production in one easy step. So I sped through that, but I'd like to thank everybody for having me here, and thank you for your time.
Thank you, sir, for sharing with us the launcher orbit system and Velo 3D end-to-end metal AM solutions. Sapphire, very insightful talk, sir. Thank you, Mr. Miller. Now, to round up the session, we are progressing into the 45 minutes interaction session of the webinar. It is my pleasure to invite all the speakers on stage for the panel discussion. We will be answering all the burning questions shortly. Finally, it is my pleasure to hand over the stage to the man of the hour, our moderator, Mr. Marc Lee, Head of IP and Commercialization, NAMIC. I request him to please take over the stage.
Thank you, Tanisha. So thank you everyone for staying online for this panel discussion. And I'm very happy to be here to moderate the session and to welcome back our speakers, Dr. Deepa, Dr. Govind, Jane, and Ali. So the panel discussion that we have, we were trying to look at the various perspectives on the disruption and growth using AM. So what does this really mean for the aerospace industry? So I've got a couple of general questions, and I thought it will be good for us to share on this discussion. So probably on the first part, why do you think generally will we use AM in aerospace? What could be the main benefits? And what is the added value for using AM in these specifications? Dr. Deepa?
Yeah, sure. I think that is a no-brainer. It's got a lot of advantages. I think all the speakers highlighted it right from the beginning. First of all, novel designs, as I said, prototypes can be made really fast. And then particularly in aerospace and space, where hotter and lighter are a very, very important buzzword. So lightweighting, of course, trying to look at the same structural load bearing with the limited material. And also, the probability of being able to get faster adoption of new alloys and chemistries. Normally, if you have to go through the conventional route, it takes a very long time. I think in this, at least you can get your alloy made into a part, tested very quickly. So I would say these are the overriding advantages of having AM and aerospace and space.
Thank you, Dr. Deepa. How about Dr. Govind? Any perspective from your side?
Yeah, see, AM, if we see from a perspective of as a metallurgist, I see very exciting, I get excited because of its inherent rapid solidification effect. And we are able to get, a consolidated part wherein rapid solidification effects are seen. So I see this AM will lead to, kind of many new exotic systems which will utilize this rapid solidification and can give very high performance materials. That is from metallurgical part. From designer part or fabrication team, I see there is a very good buy to fly ratio, means very less material goes in, and almost we get very almost that whatever final components you can get a net shape. and designer gets a very ample freedom. He is having a liberty of incorporating many things in the design. So from all that perspective, I see, that is the reason why AM can make or is making waves in all the areas.
Thanks, Dr. Govind. Ali, so how about your perspective? Because you came from the aerospace sector and you have so much experience, and even you even wrote a book on some of these technologies. What do you think is the future of this?
I think the future of this is really that we can integrate a lot more. I mean, if you remember the last picture I showed on my presentation, I didn't want to take a picture of another engine, but I guess all of us know how complex a rocket engine looks like, how complex a jet engine looks like when you open the shell. What you saw there was not a shell, was our engine. So if we consider how much we can simplify when we go additive, and of course, given that the quality, and Jean was highlighting some of the things that Velo does that I actually love, and those are the things that are enabling us that we manufacture layers on layers and yet have it simple. So I think that simplicity. I get asked that question once in a while by some very smart investors. They ask me, so why hasn't been this done before? And so many in the 90s, in fact, some of my colleagues now have looked at some of these ideas in very old days, of course, with a different perspective. So what really is changed now is that you can really have a specific cooling system like we are having in our engine integrated. These things wouldn't have been doable in the past, and so this is an opening option for many things yet to come. I think the future of it is even that we can integrate different materials when we are printing. I know another company that me and you have been talking about are printing two materials, copper and stainless steel at the same time. So then you have a lot of different opportunities, and I'm really looking forward for advancement of where Velo has came, where Meltio has came, and many other companies to take this even further to further steps, because we are going to need that.
Thank you, Ali. So probably the next question for Jean. Jean, you are muted, by the way. As a engineer as a machine maker, how do you evaluate some of these needs? And are you able to share with us how does a machine manufacturer actually identify the needs of the industry?
Well, it's a lot of talking. It's a lot of listening, and it's a lot of back and forth, trial and error. Oftentimes I have customers come to me and they don't quite know what they want, but they want to make a part. And that's really what our technical sales team is really poised on, is understanding what a customer's problem or challenge is and walking them down the path of how to get there. We're more than just a machine manufacturer. We're actually like an engineering consulting firm that we don't charge for, but we really want to enable the adoption of our technology, because we're not really out to sell machines. We're out to solve problems, and if machine sales are the byproduct of that, that's fine. But really, it's understanding the problem and knowing that you can do something to help solve those problems, and then even more importantly than just solving the problem is knowing when there's a better solution. If there's somebody that comes to me with a nut and says like, hey, can you 3D print a nut? No, you should go machine that. Don't lead people astray. Be honest with them and upfront with them.
Thank you for that perspective, Jean. Does any other speakers want to add on this?
But one thing I could say on what Jean was saying earlier, that when you talk to customers, I have been talking to a lot of customers of ours, and what you just said ignites one one quote, if I remember right, from Henry Ford, which says, if you ask people what do they want, they would say faster horses. So that's kind of relating to what you were saying. It's I guess basis of any good company to listen to their customers.
Okay. Yeah, so perhaps on the next general question to the panelists, what's your current take on the state of AM within aerospace? Is it a fair statement to say that we are moving beyond prototyping, and are the needs evolving, or is this a very unfair statement? Dr. Deepa?
Sure, I think we've definitely moved beyond prototyping. I think at a systemic level now prototyping is taking place. At individual component level, I think there's quite a bit of acceleration. In fact, there are also, I would say one step further in your question, we're looking at multi-materials and so on now, more novel ways of integrating at the system level.
Actually, I was going to pose the question to you as well on the multi-materials, because yeah, so that's one of the things that we see on the technology roadmap for the future of aerospace.
Yes.
But do you see this something that's within reach, like using technologies such as laser powder bed, or do you think it's going to use newer technologies, maybe like multi-jet fusion, perhaps?
Yeah, well, a lot of them are at the initial levels now. Some of those machines have to be built. Of course, we do know of integrated systems in terms of several companies. I'm sure Valeo is also thinking along those lines of, once you, whether it's powder bed or integrating machining, heat treatment, post-processing, multiple nozzles, and inspection systems. I think there are some systems out there now. But in terms of composite materials, metallic, ceramic, electronic circuits, I think that's where the research is going on now. At least I don't know of machines that have come out, but that's where it's going.
That's why we throw the torch to Jean to hear the perspective from a machine maker. Has there been developments that is on? I mean, that's actually announced on the open source, or do you see there's some developments in that area for multi-material printing?
So that's a great question, and I've heard that come up a lot of times from some very smart people. We have not had a strong business case for it, and to be honest, Velo is very focused on finding the business case for that. I'm sure it's going to pop up sooner or later, and then we will look at assigning resources to that. But as far as the lower hanging fruit, we haven't focused on multi-material yet. I would be very interested in knowing how you can avoid deleterious phases in your alloy. If you're mixing two different dissimilar metals together, they would have to play nicely together. And doing that properly, I think, would be a very daunting task, especially if there is a metal like, say, I want to print aluminum and titanium at the same time. These things are very, they don't play well together. They make very brittle phases. So it would depend on the alloys that you want to combine and why, and if there was a strong business case behind it.
Thank you, Jean. Dr. Deepa, I think to answer one of the audience's questions, for space applications, what are some of the key challenges that you have seen adopting 3D printing technologies, and what's the recipe for actually faster adoption of metal AM?
Sure. I think I'm going to deflect this to Dr. Govind, if you don't mind, because he directly works in the space area, and I work more in the broader aerospace. Dr. Govind, would you like to answer that?
Thank you, Dr. Deepa. So basically, in space applications, right now there are two ways that people are working to have AM as a supply chain. One is for the passive components, other one is for the active and turbopump components, or even for thrust chambers and all those things. So in space, it requires a lot of testing and qualification before, and it is almost all the sectors, but it requires space. It requires a lot of testing and qualification, not only of the components, but also of the process, and to ensure the reliability and repeatability. So right now, there is a cautious approach in the space sector. There is a willingness to incorporate AM components, but caution is about repeatability and reliability. And the second problem, what comes is the inspectability, because when the complexity increases, the inspectability also becomes limited. So these are the 3 points which need to be addressed. Before in space sector it becomes a kind of reliable supply chain. But yes, passive components, brackets, and support structures, people are identifying AM as a supply chain.
Thank you, Dr. Govind. So I would see the aspect as on the subcritical or non-critical parts. I think AM will be faster for adoption. So which brings to my next question to Ali, which AM is used in the most critical component of the rocket. And so one major question that I have is why do you think there's a need for this technology on your new type of engine in space?
Do you mean why we need a new type of engine? Is that your question?
Yes, that's right.
Yeah. Essentially, I think the type of engines that have been designed are back in 60s, 70s, as I was saying, and so which is fine, really. I mean, we have been taking a great advantage of those designs until today, optimizing them over and over. But I think what really AM enables us is generational and not only revolutionary. So having said that, I think I mean, I'm not trying to bet or triple down on AM, but essentially it's one part of it is AM, but another part of it is also that there is a new need in a space. So today we need maneuverability. Today we have so much satellites in the space that if there is a weather congestion, if there is a change in a attitude of a country, then there is other happenings and events that many other satellites need to adjust to, which we have seen recently. But also it's not only about accomplishing sending satellites to orbit, accomplishing a mission that we have defined as a country or as an agency, but it's more about the economical aspect of it, which is now I address the mobility standpoint, I address the point that we want to do something cheaper. We want to, not burn completely the entire money that we have spent. And satellites that go to GEO and MEO, they cost billions of dollars. So you want to take good care of them, and sometimes taking good care of them would mean putting better engines in there. So that's why we are trying to make them. I don't know what other panelists are thinking about it. I'm also curious, Dr. Deepa and Dr. Govind, to hear your takes on this, if I may, Mark.
Definitely. Any response from Dr. Deepa and Dr. Govind?
Dr. Govind, go ahead.
So basically, looking for more efficient engine with better IFP is always in demand. So I personally don't see any problem, but at the same time, the system should be, robust enough for aerospace. That is what generally we are looking for.
I think in our line of work, it's more not, it's like space, maybe the quantity may be small, if I may indicate. Here you need, lots and lots of repeatability, reproducibility for any new, because it's just volumes are more. So if I take, so that becomes a key challenge, particularly because of the nature of the process. So a lot of due diligence is needed, which is quite time consuming. So for example, if we take the same powder, and then we have, I mentioned briefly, but if you have anisotropy properties in one type of machine and not in the other, it's a nice publication, it's a nice report, but in the field, how do we address that? Now, of course, we have a solution there in easy adoption. And namely, that is a casting is also full, we've been doing castings for 6-7 decades, flying planes and spacecraft quite successfully. So I think we need to sort of look at it very practically, given the factor of safety, and go in full-fledged in implementing these new materials. I'm not sure if I'm answering in the same line of thought, but I wanted to distinguish, space and aero engines, particularly aerospace, with the quantity, with the volumes in this context.
Thanks. That's an interesting take on it.
Thank you. Thank you, Dr. Deepa, on that. So, which actually partially answer one of the questions that's posted by the audience on how much of the constraint is presented by the availability or unavailability of custom metals for AM. So probably I can pose a question to Jean. Do you think that there needs to be a need for a separate innovation in this area, and whether it's already being handled by the current AM industry?
Yeah, that's another really good question. And, I know that there are people out there that really need a lot of different metals. And the challenge that we have right now today is the fact that our machines are millions of dollars. And if you need one part printed in, say aluminum, but then you need another part printed in copper, but then you need another part printed in Inconel or whatever it may be, the powder swapping alone is a risk of cross-contamination and difficult enough, even if you do it on one machine. Or if you do it on multiple machines, you're talking multiple millions of dollars for, 5 parts possibly, which is not realistic. So, I think eventually, yes, there could be room for something like that if someone did come up with a unique and novel solution to that. I know that we're not quite there yet, but yeah, that could be a bit of a game changer if there is, a viable and cost-effective solution.
Yeah, I think the industry is actually evolving and coming out with new methods to produce this kind of custom-made metal powders. So I'm actually wary of the time, and for the questions that are not answered, we will reach out to the speakers, or you could write in to us. So once again, thank you to the speakers for coming on the panel. I'll let the MC round off from here.
Thank you so much, Mr. Lee. So now we have come to the end of our webinar session. On behalf of IIM and NAMIC, I convey my most sincere thanks to all the speakers who have given their valuable time from their busy schedules to grace this webinar and share with us their enriching opinions. If you would like to reach out to our speakers, IIM or NAMIC, you may contact us via the email on screen, and we will do the necessary introductions. Thank you once again, and we hope to see you at our next event. Have a good day.